All right, today we are diving deep into something called molecular orbital theory. Now, I want you to think of it like a quantum dashboard for molecules, a control panel that lets us see exactly how they're built, why some are super stable, and what gives them all their wild and unique properties.
But to really get why this is so cool, let's start with a puzzle. You've seen magnets stick to your fridge, no big deal. But what about a magnet sticking to a liquid? It sounds nuts, but if you pour liquid oxygen between the poles of a powerful magnet, it just hangs there. It's magnetic. The usual models of chemical bonds, the ones with sticks and dots, they have absolutely no explanation for this. To solve this mystery, we're going to need that new dashboard. So here's our game plan. First, we'll get a feel for the quantum dashboard itself. Then, we'll learn how to actually build molecular orbitals, which are kind of the foundation of the whole thing. After that, we'll see how to arrange them on an energy ladder, learn to read the dials to make real predictions, and finally, we'll put it all to the test and crack the code on oxygen's weird magnetic secret. So to solve our puzzle, we need a way better model. We have to go beyond just drawing dots and lines. We need to start thinking about electrons as what they really are, waves occupying these three-dimensional regions of space called orbitals.
Okay, so what actually happens when two atoms get close enough to form a molecule? Well, their individual atomic orbitals don't just, hang out next to each other. They actually combine, they merge, and create a totally new set of orbitals that belong to the entire molecule. And we call these, you guessed it, molecular orbitals.
Now here's the magic trick, and it's a fundamental rule you gotta remember. If you start with two atomic orbitals, you have to end up with two molecular orbitals. They split. One of them becomes a lower energy, super stable orbital we call a bonding MO. This is the glue holding the atoms together. But the other one becomes a higher energy, unstable antibonding MO, which does the exact opposite. It actually works to push the atoms apart.
So how on earth does this split happen? Well, remember, electrons act like waves. So when two of these orbital waves add up, that's called constructive interference. Think of two ocean waves combining to make a bigger one. They create a bonding orbital. All the electron density gets packed between the two atoms, pulling them together. But if the waves subtract from each other, destructive interference, they cancel out, creating something called a nodal plane. That's a zone with zero electron density right between the atoms, which pushes their nuclei apart and creates that high-energy, unstable, antibonding orbital.
And this table just lays it all out perfectly. Bonding orbitals, they come from wave addition. They're the low-energy glue. Antibonding orbitals, you'll see them marked with a little star and an asterisk. They come from wave subtraction. They're the high-energy anti-glue. It's really that simple. For a molecule to even exist, the glue just has to be stronger than the anti-glue.
Okay, so we've made our new molecular orbitals. What now? Well, now we have to arrange them in order, based on their energy levels. The best way to think about this is like building a ladder. Electrons are lazy. They're always going to fill the lowest rungs first and then work their way up.
Now, these orbitals can overlap in two main ways. When they meet head-on, kind of like a direct collision, they form what we call sigma bonds. But when they overlap side by side, or laterally, they form pi bonds. As you can probably guess, that direct head-on sigma overlap is way stronger. So the sigma bonding orbital is usually lower in energy than the pi bonding one.
Let's see how this all stacks up. For a lot of common molecules, like the oxygen we're trying to figure out, or fluorine, we get this standard energy ladder that you see right here. It starts at the very bottom with the lowest energy orbital and builds all the way up to the highest. This is going to be our blueprint.
But chemistry always has a twist, right? It turns out that for the lighter elements, we're talking everything from lithium up to nitrogen, there's a little complication. A weird interaction between some of the orbitals actually pushes that sigma 2p orbital up in energy, making it swap places with the pi 2p orbitals. It's a small detail, but it's a crucial one that shows you just how sensitive this model really is.
All right, we have built our ladder. Now it's time to actually use our dashboard to get some data. We're at the point where we can predict if a molecule will even form, what kind of bond it'll have, and even whether it's magnetic or not.
So our dashboard has two key readouts. First is what I call the stability logic gate. Do you have more electrons in bonding orbitals than in anti-bonding ones? If the answer is yes, congrats, you've got a stable molecule. Second, we can calculate something called the bond order, using the formula you see here. Let's run a quick test on a hypothetical helium molecule, H2. It would have 2 electrons in bonding orbitals and 2 in anti-bonding. Plug that in, and you get a bond order of 0. That means no stable bond forms, which is exactly what we see in the real world.
And this bond order isn't just some abstract number. It tells you real stuff. A bond order of 1 is a single bond, 2 is a double bond, 3 is a triple bond. The higher the bond order, the shorter and stronger that bond is. But most important for our mystery, Check out the magnetism toggle. If every single electron is paired up with another, the molecule is diamagnetic. It won't care about a magnet. But if it has any unpaired electrons, it becomes paramagnetic. It's attracted to a magnetic field.
Okay, this is it, the moment of truth. We have our dashboard, we know the rules, and we have the right energy ladder for oxygen. Let's fire this thing up and finally solve this mystery once and for all.
Okay, so one oxygen atom has 8 electrons, which means an O2 molecule has 16 total. Now, following our rules, we fill up that energy ladder from the bottom, 2 electrons per orbital. We fill up the 1s, then the 2s, then the sigma 2p, then the pi 2p. That's 14 electrons so far. We have 2 left. So where do they go? Well, they have to go into the next available rungs on the ladder, the pi antibonding orbitals, the ones with a little star. And here's the kicker. Because those 2 orbitals have the exact same energy, the electrons don't pair up. One goes into each.
And boom, there it is. That's the answer. Because of those 2 lonely, unpaired electrons sitting up there in those antibonding pi orbitals, molecular orbital theory predicts that oxygen absolutely must be paramagnetic. The dashboard works. Our model perfectly explains a real, weird, observable fact that the simpler theories just couldn't touch. Mystery solved.
And this is why this theory is such a game changer. It's not just a bunch of abstract rules. It's a predictive powerhouse. It gives us the right answer for oxygen's bond. It's a double bond, and it correctly predicts its magnetic behavior, which, again, no other simple model can do. It's just incredible. So let's just quickly recap the big ideas here. Atomic orbitals combine to form molecular orbitals. We can figure out if a molecule is stable and what kind of bond it has using that simple bond order formula. And the crucial takeaway for today, if you see unpaired electrons, you're looking at paramagnetism.
We've just seen our quantum dashboard solve a really strange puzzle with amazing precision. And it kind of makes you wonder, right? If it can do this, what other molecular secrets are just out there waiting for us to unlock?